Okay, so this was a perfect introduction to this very short presentation as well. It's about the hardware implementation of the brains of these embodied robots, or if you want, spiky neural network chips. Just one quick slide to point out the differences between how real brains do computation and how standard computers do it. As you know, real brains have different computing elements that have different morphologies. They use the physics of their substrate to do computation, and they use physical time to do computation, which is completely different from the way that accelerators, microcontrollers, computers run neural networks, where they simulate by running numerical integration methods to solve differential equations in a way that is completely decoupled from physical time. So you could take days to run a simulation that in reality would take a few milliseconds, or you could run evolutionary algorithms in seconds, whereas, as you know, it might take ages in real physical time. So by using analog circuits that are inspired by the brain, we actually try to bring back a physical computation with physical time directly on silicon. And so to do that, we need to understand how the brain does it first. So we study really neuroscience, neuroanatomy. We try to derive from the neuroanatomy the models, also by looking at AI, artificial intelligence models that can carry out different types of computation that are useful for robotics, from even filtering or measuring the angle of a joint to controlling a robotic joint, to making decisions and controlling everything with silicon neurons, and by connecting them together using analog circuits for doing the dynamics, and then digital circuits for actually connecting neurons together, we can actually emulate the biophysics of neural systems. And we try to see if we can get some intelligence, or if you want, cognitive performance out of these chips. But as every one of you well know, it's not possible to do that just by looking at a chip sitting on a desk. You need to embed these, embody these into robotic platforms that can operate in complex environments. And by having the interaction in real time, in closed loop, then maybe something can emerge out of these chips, especially if these chips also implement on-chip learning. We've been doing these types of things for several years. Josh knows well. We go back when he was also in Zurich. The latest chips go back to the 2000s, where we had tens, 30s, 50 neurons. Then we've been writing Moore's law, where we could put now thousands of neurons, and maybe now we have tens of thousands of neurons. And if you just look at the circuits are a combination of analog and digital. Maybe I can zoom in here. You might recognize, sodium channels, potassium channels, after hyperpolarizing current channels, leak channels. These are all analog circuits. And then whenever the action potential is generated by these analog circuits, then we convert those into digital events. So we have also mixed signal, analog and digital, which are used for routing, for communicating. And then, as I said, we can put thousands of these neurons on. And if you have a particular neural network that you think could be used to do a CPG, or to do sensory processing or motor control, we can actually connect these neurons together through synapses, through different nonlinear properties like short-term depression or spike frequency adaptation, and implement some computation. One criticism that is often asked to us, also from roboticists, is why spikes? Why should we go to the trouble of doing this? And by people that, like you, are building systems, I think it's very, very easy to explain. Remember, the goal of our approach is to process sensory signals in a low power and compact way, in a closed loop way. So we want to do the sensory motor processing in the most efficient way. We want small volume, small power consumption, and real-time closed loop. So, and we want to be able to send signals from, for example, joints far away to a processing unit through some wires, cables, through noisy communication channels. We want to do this in a robust way, and we want to do it with low power and latency. So if you put all of these ingredients together and you just open your communications textbook, you will find that the most efficient communication protocol to transmit signals through noisy channels by minimizing power and bandwidth is to use pulse frequency modulation. This is going back, to Shannon, to the 60s or even before. So this is just the optimal way to build communication of analog signals across noisy channels. It's no surprise that nature found the same solution, and spikes are everywhere, you know, from small insects to elephants. In addition, once you have spikes, you can actually use them to do computation. Not only you can integrate them over time and recover analog rates, but you could look at correlations, spike timing, and so on. So you have these extra degrees of freedom. Now, the other question is why analog circuits? In addition to being small and low power, they have the problem of being noisy. And this is a criticism that is, you know, always brought up also by, not only by AI experts, but also by roboticists. And I just wanted to point out that there is a way to cope with these noisy analog circuits and to do robust computation and robust motor control. For example, if we just take these 256 neurons that are on one of these cores that I showed you, you will see that the first time to first spike is not precise. There's a huge variance. It's actually around 20% coefficient of variation. So what can we do to do robust and reliable computation? You know, if you want to control an airbag with these devices, well, the most obvious thing, you just average. If you take an average over space, and if you average over time, if this is a periodic signal, if you're creating, I don't know, 50 hertz or 100 hertz, you can average over both. And we try to quantify, you know, how much do you gain by averaging using our chips? And we saw that if you have clusters of neurons of even 2 or 4 or 8 neurons, you can decrease the coefficient of variation. So in this case, it's about 20%. For 2 neurons, it's 18%. But if you have already 8 neurons, you can have a coefficient of variation, which is, you know, around 7 or 6. And once you have the coefficient of variation, you can calculate the equivalent resolution in bits. And so here you see in color scale, the bit resolution, which goes from 4 bits to 14 bits. So depending on the size of the population of these clusters, you can at runtime decide to have a very fast and coarse outcome, or you want to have, you know, you want to accumulate evidence, integrate more. And so if you integrate over time, but also collect more outputs of more neurons and have a higher precision. So this brain-inspired approach allows us to recover some of the precision that you usually have with your Arduinos or other standard digital microcontrollers. So we've been doing these chips for many years. We don't want to replace microcontrollers or CPUs or GPUs. There are advantages that you have low latency and sub-milliwatt power consumption. People always say it's low power, but you have to quantify. So these chips typically have microwatt power consumption figures. So if you want to, you know, have like salt and pepper, just distribute them around your soft or hard body, you can, and they would still, you know, even tens of them would still burn less than a milliwatt. But they do have low resolution. They are susceptible to noise. And so it really depends on the type of application that one wants to do. And closed loop, as soon as you have negative feedback, you know well that even if you have a slightly more than chance output, by closing the loop and by having active sensing, you can then iteratively reduce the error more and more. So robotics is a perfect application for these types of chips. And as I said, they're good for closed loop sensory motor processing, low dimensional multimodal signal. You can, if you have cochleas, retinas, pressure sensors, you can all convert those into spikes, and it's very, very easy to do sensory integration and fusions of multimodalities. But they are not good at number crunching, like, you know, Excel sheets or matrix inversions or matrix multiplication. So they are not supposed to replace GPUs and CPUs. They're really useful for specific sensory motor processing applications. We've been using them mainly for sensory applications, and another killer app is biosignals, because they have the same dynamics of natural biological signals. So we've been using them to decode the measurements made on zebrafinch, to recognize the song of the bird by listening to the neurons of the real birds. We use them regularly to classify EMG signals and then control prosthetic devices, or we connect them to real neurons and monitor, for example, in this case, is for detecting the epileptogenic zone and trying to understand which part of the brain is the one that is responsible for creating epileptic seizures. To give at runtime during the operation, the surgeon an extra clue on which area of the brain he or she should resect to cure the patient. And of course, we connect them also to robots. This is a very simple example that many of you probably have done in your career. But what we did is we connected a vision sensor, which is a silicon retina that only produces spikes in response to changes. These spikes go to populations of silicon neurons that are responsible for left or right sensory input. So if there is activity on the retina on the left, there is a left population. And if there is activity on the right, there's a right population. And then essentially it's a Breitenberg vehicle. We connect the left sensing neurons to the right motor outputs and vice versa. It's a winner take all, so you cannot do both left and right. If there is a population of left neurons active, it will inhibit the right ones. That's to improve, performance. Also, if there is any obstacle, either left or right, we inhibit the speed neurons, which are otherwise always on. There is a recurrent population that's saying, go as fast as you can, unless you're inhibited. And this very simple neural Breitenberg vehicle behaves nicely. If there is time, I can show you the video. But you can imagine that you can add decision-making models. You can add more intelligence by having extra populations of neurons that either integrate multiple inputs and then connect with extra inhibitory or excitatory connections to the motors. So this is just sort of the first step in which we only have reactive control, but you could add more cognitive type of control where you could have the internal state of the robot and maybe some drive or motivation to bias the motion and make it go wherever it should. So here is a small video. You should see here the activity of the retina, and if you see that it's on the left side, the right population motor neurons will be more active, and if it's on the right, the left population motor neurons, and the speed signal also should decrease. And here you see it from the top, and you see the robot moving around. We have a can, it detects it, so there are some spikes. The spikes are very sparse, which means that every spike is a few picojoules, and if you have tens of them, you might get to total consumption microwatts. But this is just to give you the idea that we don't have any bandwidth limitation. It's not like when you have a high resolution camera and you need to transfer all of the data out. This is just a small number of bits per second that needs to be sent out of the chips to the neuromorphic processor. And the neuromorphic processor neurons, you can integrate their spikes into some analog value, and depending on that, that can go to the motor controller that can drive the motors. And so you see it's doing its thing. It's avoiding even very difficult visual scenes that have shadows and thin bars are not a problem for this particular technology. So again, this is a toy problem, but it's just to give you an idea of what can be done with these chips. And I really like the idea that we can now embody them directly on hardware, not in simulation, and use them to run these attempts to try to find the optimal solution or the optimal body. So finishing off, this is not work that I did myself. I'm very fortunate to have a very diverse and talented group of postdocs and PhD students, and of course, the funding agencies that have been supporting the design, implementation, and testing of these chips, both the Swiss and the EU agencies. So thanks for your attention, and I think I leave time for questions during the panel discussion.